Hi, my name is Kyle. I'm an engineer at Development Seed, and I'll be talking today about Geoparquet and Geoarrow in deck.gl. I want to start with some motivation on why you should care, get into a little bit of the background of Geoparquet and Geoarrow. Not planning to get quite as deep into the format. Actually, it's nice that Paul showed you that overview. Uh, if I have time at the end, I'll give a demo with a little bit more detail in the format. But I want to talk about why deck.gl is really useful in combination with Geoparquet and Geoarrow, why they all mesh together really well, talk about some implementation status and some future work. So starting with motivation, I gave a similar talk to this a year ago in Madrid, and I really motivated that talk with deck.gl at the center of how do we get the best deck.gl performance with vector data. If you look at the optimization guide, it says you should use binary data, but the binary API is kind of hard to use. You have to use low-level array buffers and format your data in the offset kind of setup that you need for polygons. And that it happens that Geoarrow simplifies this and that Geoparquet is the best way to get that into the browser. But here, I think in the last year, Geoparquet and Geoarrow have matured a lot. And so I think that Geoparquet and Geoarrow on their own interface really well with each other. And it just happens that deck.gl is also best positioned to make use of this at scale for data visualization. So Geoparquet is a really efficient format for geospatial vector data. Geoparquet builds upon Apache Parquet. So first we need to introduce this Parquet data format. It's really the de facto columnar file format for tabular data today. It uses a chunked columnar format. So if you have, say, 10 million rows in your file, you might break that into 10 chunks internally. The first chunk contains all of the columns for the first million rows, then the next million rows, and so on. This is in contrast to like CSV, which stores all the data for the first row, then the second row, and so on. It has a really extensive type system, including nested types. So you can have lists or structs as individual columns as part of your table. It has really, really good compression. So it generally compresses better than any other tabular data format. There's lots of widely adopted implementations. Python, C, Java, Rest have been around for a while. I use the Rust implementation to have a WebAssembly module that can read and write this in JavaScript. And in the ecosystem, it's been really widely adopted in big data systems, data lakes, data frame libraries, and cross-language. Geoparquet is an initiative that started a couple years ago. It's recently been added as an OGC developing standard. And so there's lots of people who are excited about having a spec for how do you store these geometries inside of a Parquet file. It's not extending the file format itself. So anything that can read Parquet can also read a Geoparquet file in case you want to work with a non-geospatial data inside of it. But then Geoparquet is usable by a lot of these geospatial tools. In the Python ecosystem, you have GeoPandas, as well as GDAL that supports reading and writing Geoparquet. And so most of the geospatial ecosystem works with GDAL and is able to use this data. It's cloud native in the sense that you can have large files in the backend that you can read portions of the file with HTTP range requests directly from the front end without having to fetch the entire file. And so that's really powerful because you can use the same data both for analysis on the backend as you're using for front-end visualization without having to make multiple copies of the data. The specification is at 1.0 release candidate. So let us know if you find issues with the spec. Spatial partitioning is not yet part of the specification. So that's something that we plan to have in 1.1, but the data format is really useful still before then. there's a huge community that's working on integrating this file format, and so I think that Geoparquet on its own will become very widely used in the next few years, and it's already really useful in the browser for some reasons that we'll get into later. Then I also want to introduce what Geoarrow is, because it's really, I think, going to be impactful alongside of Parquet, but in different avenues as the Parquet format. And it's really around being able to share data between systems without having any serialization, and at times without even copies. To start, I actually want to rewind a while back to 2006 when the Python buffer protocol was implemented, because Jake Vanderplas, who's written some books on data science in Python, has really said that the buffer protocol is why Python is the environment that it is for scientific computing. That it allows you to share multidimensional array data between Python libraries without having any copies. You're able to point to specific locations in memory where you have your C arrays and not have to go through Python, which might slow things down. And so that enabled a ton of innovation on top of NumPy. And then we have the issue of, well, we have pandas, we have all this data frame ecosystem that's being built on top of Python, but we have a similar issue where when people wanted to use Python and R and these other systems, you have to convert to, say, CSV to move data between systems. So if you go to the Arrow documentation, you'll see these two images on the right-hand side where you have lots of different ecosystem tools that all are using tabular data, but there is no interoperability between them beyond having a separate importer and exporter between every format and every tool. And so what the Apache Arrow project is really doing is defining a memory stable, ABI stable format for zero copy sharing of columnar tabular data between all of these different systems. And so it's powerful because you can use the same data between, say, Python and R without having any memory copies at all. And so now I think this is really the standard for all of the new crop of libraries that's coming out now. You have pandas in V2 is now implemented on top of Arrow. You have polars, these new databases like DuckDB that are using an Arrow compatible columnar storage. And to tie this back to Parquet, when you load a Parquet file, you get Arrow memory. So Parquet and Arrow are very tightly intertwined. As an example on how fast it is to move this data, this is an example from a blog post of showing moving data between Python and R, that when you had a data frame that you had to copy, you have ON time complexity. But then when you're using an Arrow data frame on both sides, it's just changing the ownership of the pointer, and it's completely free, essentially, to move data between Python and R. And so in geospatial, we really have the same issue of we have all of these tools. You can paint the same picture in the top right of we have data frame libraries, we have databases, we have systems on Spark, we have file formats. And right now, it's really difficult to move the data in between all of these different implementations. And so Geoarrow has been under development the past few years, and it allows all of these geospatial tabular data systems to talk with each other. In Python, there's a protocol that's been around for a little while called GeoInterface that tries to solve some of these problems, but it says any package that any class that defines this function will return GeoJSON data. And so that's great because it allows packages to talk to each other without knowing anything about the other package, but making everything GeoJSON is really, really slow. And so what Geoarrow is essentially is defining a binary, really efficient, really fast way for all of these geospatial packages and across languages to talk with each other without having to do any serialization. And so Geoarrow is defining this columnar way to store geospatial vector data in Apache Arrow. It's pretty new. It's not as widely implemented yet as Parquet, but a huge thing happened a year ago when GDAL 3.6 was released, where GDAL can read any vector format that it supports as a GeoArrow table. And so if you're in Python, you can read from GDAL and then move that data into R without any copies. And so I think it's really starting the beginning of this ecosystem where GeoArrow is used now in QSpatial and DuckDB Spatial, as well as close integration with GeoPandas. And here, to tie this back to Geoparquet, as Parquet gives you arrow memory, loading Geoparquet gives you GeoArrow memory. So I think that now that I've introduced Parquet and Arrow, I want to say why deck.gl is really uniquely positioned to take advantage of the potential impact that Geoparquet and Geoarrow are both going to have in the ecosystem. So my argument for why deck.gl and Geoparquet is because deck.gl is really focused on supporting large vector data sets in the browser, but that loading large data sets, usually the limiting factor in total time is how long it takes just to download that data from the internet into your machine. Because Parquet files are really, really efficient at compression, Parquet files tend to be a lot smaller than comparable formats, and just the smallest way you can get vector data into the browser. Also, you can load less data if you only need a couple columns. If you need, say, an attribute column or two plus the geometry column, you can load just those 3 columns, even if the file on disk has 100 columns. In the future, when we have spatial partitioning as part of the specification, you'll be able to fetch just a small region of your data set directly from the browser without having any server in between. And because this file format is so well supported on the back end, you can use the exact same data files both for front-end visualization and for back-end analytics. And then why is deck.gl so well, has so much potential with GeoArrow is because deck.gl has an existing binary API that you should use whenever you want the best performance out of deck.gl. And it happens that deck.gl's binary API uses a columnar format already. So here, for example, taking the slide from one of Xiaoji's presentations, you can look at the instance positions attribute, which says where should all of the points in the layer be located. And if you want to render 100,000 points, you have a single buffer that has 200,000 values for a 2D point array. And so it happens that GeoArrow's binary columnar format aligns very well with what deck.gl already supports in its binary API. And beyond that, deck.gl has had a prioritization on supporting large data for a long time. So it's like you've heard today that we're investing in next generation technologies like WebGPU. And so I believe that no other visualization framework that focuses specifically on the data visualization is as well equipped to support this as well as deck.gl is. And the scattered plot layer, path layer, polygon layer, each of these are already able to support these GeoArrow data formats that exist today. As one more use case to really motivate this, we talked about PyDeck in the last talk of how like PyDeck is amazing, but it's not always the most performant because from Python, if you have a data frame, it serializes that to GeoJSON to copy into the web browser to render. So GeoArrow is powerful because you're using the exact same memory format in every step of the process. So if you have data in GeoPandas or GeoPolars, another data frame library I'm developing, you can move that from GeoPandas into JavaScript by a Jupyter widget without any serialization, into deck.gl without any serialization, into the GPU without any serialization. You just need a couple of copies to get the data from Python to JavaScript into the GPU. And if your Python session is remotely, say in Colab, then you might want to do the bottom part of the screen where you serialize into Geoparquet, which is really efficient from Geoarrow to Geoparquet. You have a lot smaller file size for downloading into the browser. You efficiently deserialize that back into Geoarrow, and then you have a straight memory copy to the GPU. Talking a bit about implementation status, I have a Parquet library called Parquet Wasm that uses the Rust implementation of Parquet. Here, I tested with a Geoparquet file with 7 million coordinates, and on my machine, it parsed in 1.3 seconds. This library includes, it's very modular in what you want to include in the library if you're compiling it yourself. So it's as small as 300 kilobytes if you don't include any compressions. It's a little bit larger than that if you include compressions. All of the compressions in the Parquet spec, LZ4, ZSCD, gzip, Brotli, are included in 741 kilobytes to read that. Geoparquet Wasm extends Parquet Wasm just to decode the WKB encoded geometry column into a Geoarrow geometry column. I've been working on this lately. It's finished. I just haven't quite published it to NPM yet. So this will be nice to have specification compliant Geoparquet files that parse exactly into Geoarrow files without any extra JavaScript land work. On the deck.gl side, everything is there to render these tables directly. So on this side, you can see that we can access the raw arrow memory as a float64 array, pass that data into the scatter plot layer as an array directly via the get position attribute, and pass that into the scatter plot layer. And it's really fast. Here, this is 3.2 million points rendered in deck.gl. This is one of my observable notebooks that I'll show a link to at the end. And if we have time, get into those a little bit. But there you can see an example of loading Geoparquet and getting this in the browser. I want to talk a little bit about how I think this can progress further. For one, it's a little bit difficult usability-wise to use this because you have to use the low-level deck.gl API directly. For most people, it is difficult to use the low-level API. So I'm really hoping that we can talk about and work on a Geoarrow layer where a user only has to import, say, Geoparquet Wasm, load a Geoarrow table, pass that Geoarrow table into the Geoarrow layer, and similarly to the GeoJSON layer, this layer renders the sublayers for the point, polygon, line string layers automatically. Hopefully in the future, this could have better integration as well with picking and styling, but as an initial implementation, just having something simple that can minimize the manual effort that the user has to do would be really powerful. Another thing in future performance is in getting the data from WebAssembly into JavaScript. So my parser is a WebAssembly-based parser. And WebAssembly is amazing in that it lets you use all of the code written for C, C++, and Rust without having to rewrite it in JavaScript. But one downside is that WebAssembly, being sandboxed, has a different memory space than JavaScript. So in order to get the data into JavaScript to be used with deck.gl, you need to somehow get the table from WebAssembly into JavaScript. The easy way to do that is to have some serialization. You have a table, you serialize it into a single buffer, you copy that single buffer into JavaScript. But there, the downside is that you're making an entire memory copy of your entire table in WebAssembly before you copy it out, which doubles the peak memory utilization on the WebAssembly side. But the point of Arrow is for every implementation of Arrow to have the same memory format. So we don't actually need to have that copy. One thing that I've been working on is parsing the WebAssembly table directly from the WebAssembly buffer without copying without any serialization. So what we can do is have a view directly into the WebAssembly memory space, but that works with Arrow.js. You can either view it directly or copy the individual arrays, which is way more efficient still than an extra serialization step, and essentially reduces that WebAssembly memory pressure by half. Another piece of work on the bundle size, the Arrow.js library is a few hundred kilobytes, or 200, I forget the exact number, but in some cases people don't want to incur that bundle size. As part of the work to read and write Arrow data in WebAssembly, I have some very minimal Arrow array definitions. So at least in theory, it would be possible for the Geoarrow layer to avoid a hard dependency on Arrow.js. So if an application had a WebAssembly-based Arrow table or data frame library, you could use that directly with the Geoarrow layer without having that bundle size penalty.